What if numbers could rotate, reflect, and stretch all at once? Welcome to the world of complex numbers, where algebra meets geometry and symmetry becomes your superpower. Let us start from the basics. A complex number is any number that can be written in this form: a plus ib. Here a is the real part and b is the imaginary part. The symbol I is the imaginary unit, which is defined by I square is equals to minus 1. This definition allows us to solve equations like x square plus 1 is equals to 0, which has no real solution in real numbers. Every real number and every purely imaginary number is also a complex number. Now, we look at one of the most important ideas, which is powers of I. They repeat every four terms. I raised to 1 is I raised to 2 is minus 1, I raised to 3 is minus I, and I raised to 4 is 1. So instead of calculating large powers directly, we can use the remainder when the exponent is divided by 4. So the general rule for I raised to n is I raised to n mod 4. After doing this, if the remainder is 0, then replace it with 1. If it is 1, then replace it with I, 2 then minus 1, and 3 then minus I respectively. Now, if two complex numbers are equal, then their real parts must be equal and their imaginary parts must also be equal. So if a plus ib is equals to c plus id, then a is equals to c and b is equal to d. This rule is used to find unknowns by comparing coefficients. Now let us look at the algebra of complex numbers. In addition and subtraction, it is done component wise. That is, real with real and imaginary with imaginary. For multiplication, we expand normally, but remember I square is equals to minus 1. For division, we multiply the numerator and denominator by the conjugate of the denominator. This removes I from the denominator. Now let's look at the conjugate of a complex number. So the conjugate of a complex number is obtained by changing the sign of the imaginary part. So if z is equals to a plus ib is a complex number, then its conjugate is a minus ib. Conjugates also give us some useful properties, like z plus z conjugate is times real part of z. Z minus x conjugate is 2i times imaginary part, and the multiplication of z with its conjugate is square of its magnitude or modulus. So the modulus or magnitude of a complex number represents the distance from the origin on the Argand plane. So for a complex number z, which is a plus ib, the modulus or magnitude is root a square plus b square. It behaves like distance, so it is always non-negative. Also, can separate it for multiplication and division cases like this. In the Argand plane, the x-axis represents the real part and the y-axis represents the imaginary part. So a complex number a plus ib is represented by the point a comma b. Distance formulas become modulus expressions. So mod z is the distance from origin to the point z, while mod z1 minus z2 is the distance between 2 points. Every complex number has magnitude and a direction. So the direction is given by the argument theta, which depends on the quadrant. In polar form, z can be written as this: r to cos theta plus I sin theta. where r is mod z, that is the modulus, and theta is argument of z. Using Euler's formula, we can write it as z is equals to e raised to r into e raised to I theta, uh, where e raised to I theta is nothing but cos theta plus I sin theta. So the polar form becomes r into e raised to I theta. Euler's formula connects exponential functions with trigonometry. So it states that e raised to I theta is cos theta plus I sin theta, which makes polar form extremely compact and powerful. Now, De Moivre's theorem. It tells us how to raise a complex number in polar form to any power. So we simply raise the modulus to the power and multiply the argument by the power, that is z raised to n equal to r raised to n into cos n theta plus I sin n theta. Now let's look at the roots of unity. So roots of unity are solutions of z raised to n is equals to 1. So these roots lie equally spaced on the unit circle and show perfect symmetry. Their sum is 0 for all n greater than 1. Now let's look at summation using complex numbers. In summation problems involving powers of I, the key is cyclic repetition. We break the sum to blocks of 4 terms and simplify each block, as we saw earlier in powers of I. Now some geometrical transformation. So multiplication by I rotates the point by 90 degrees in anti-clockwise direction. Multiplication by minus 1 rotates it by 180 degrees. Then taking its conjugate reflects it across the real axis, that is the x-axis, and then multiplication by e raised to I theta rotates it by theta. A locus describes all possible positions of a complex number satisfying a condition. So most locus problems reduce to circles or straight lines. For example, mod of z minus a is equals to r represents a circle, while mod of z minus z1 is equals to mod of z minus z2 represents a perpendicular bisect. Now let's look at triangle and area using complex numbers. So using complex numbers, we can calculate the area of triangle using a single formula, which is half of imaginary part of z2 minus z1 into conjugate of z3 minus z. So this gives area of the triangle and it avoids coordinate geometry and is very efficient. These are some inequalities in complex numbers. These come directly from triangle geometry. For example, the triangle inequality, this mod of z1 plus z2 is less than equal to mod of z1 plus mod of z2, and reverse triangle inequality is mod z1 minus mod z2 is less than equal to mod of z1 minus z2. They help us bound expressions involving modulus. So think of these like sides of triangle.